So that goes into how we calculate fault currents, okay, at least on paper. I will see that for large networks, we will do it a little differently. So before we can calculate these fault currents, we have to know the system impedances, reactances for different transmission system components, like transmission lines, how to represent a generator in a very simplified manner for these fault studies, and how to represent this transformer here. All right. So if you assume a perfectly transposed transmission line, then the positive and negative sequence impedances are equal. And they can be calculated by a program such as EMTDC. These impedances can be calculated. Perhaps they can be calculated by hand. Not perhaps, they can be. But the best would be to make use of this program such as EMTDC. When it comes to zero sequence, it involves ground return. So this zero sequence impedance is always greater than positive and negative sequence. And again, we can use a line constants program such as this EMTDC. All right. Now, when it comes to generator, a very simplified representation of a generator is a positive sequence network where you have a subtransient reactance because we are dealing with fault currents which are for a few cycles since the inception of the fault. So because the dampers damper windings which are present in these generators, we usually talk about subtransient reactance because we have steady state reactance, we have transient reactance, and we have subtransient where the damper winding currents also play a role. So we use those here. So we use a network which consists of this subtransient reactance, and there's a voltage source behind it, such that together they yield the pre-fault voltages and currents in the network. Okay, so that will be the representation for the generator, and for the positive sequence reactance. If you think of a round rotor machine, it's the d-axis, or even if it's a salient point machine, you may simplify it and just use the d-axis subtransient reactance. And the negative sequence reactance is usually, it can be approximated as the average of the d-axis subtransient reactance and the q-axis subtransient reactance. The reason is that in the negative sequence, the rotor is, let's say, rotating in the positive sequence, but these negative sequence components are rotating in the opposite direction. Okay, so it's damper windings again play a role there. All right, when it comes to transformers, their leakage impedances are determine the positive and negative sequence impedances or reactances. But when it comes to zero sequence, it depends upon how these transformers are connected. Okay, so let's look at this way here. Let's say your transformer connected in a delta. So there are three diagrams here. It's not very clear, but there are three diagrams here. So if a transformer was connected, if a load was connected, let's say, not even a transformer, just a load, well, it could be a transformer here, connected one set of windings like this, then there's no way these three currents can flow, because from Kirchhoff's current law, they'll add up to 0. Similarly, there's no way that any current can flow. Zero sequence means all of these currents are the same. Okay, not only in frequency, of course, as a line frequency, but in phase they are the same. Okay, so you add up these, and they, by Kirchhoff's current law, they should add up to 0. What that means that all these three being equal to each other individually, they are equal to 0. Okay, so no current can flow here. Similarly, these three currents should add to 0 and they're equal to each other. What that means is no current can flow in a, let's say, one of the set of windings in a transformer was connected like this here. Now, what happens if you have this Y is grounded, right? But so that's say primary winding, and the secondary winding is has this it's connected in a delta. Okay, so now these currents can flow because now there is a path for this current to circulate like this here. Okay, so that is possible. So you could have delta here, or you could have another, instead of this delta over here, if you had a winding like this, then again, in addition, let's say this is primary and this is secondary, then these currents can flow. So quite often, not quite often, but sometimes anyway, this neutral here may be grounded through some grounding impedance Cn over here. So in that case, the zero sequence network that you will get, these three currents being equal to each other, you get 3 times Zn in series with this zero sequence impedance here. So this is the zero sequence network that we will have. Okay. So here is an example, one-line diagram of a simple power system. Prior to fault, these are the voltages here given, the load is given, various impedances are given, and some fault here takes place here. It could be single line to ground, or it could be three-phase symmetric fault, and the transformer connections are given also here. So we should be able to calculate what these fault currents should be, or would be. But we are not going to go into that, but using the approach that we have discussed, we ought to be able to do that. So in this course, we have often looked at a 3-bus system as shown here, and perhaps there's a fault over here. So we can, of course, do it with paper and pencil because it's a very simple network, but the best thing is to take this and put it in a program like Power World. Okay, that's a very good program to calculate these things. But there are certainly other programs available, especially for setting the relays. There are a couple of widely used programs which could be implemented. But the procedure that we have outlined is not what is used when we are talking about large networks consisting of thousands of buses. So we have learned earlier how we can express the system in positive sequence, assuming a balanced system in terms of this Y matrix over here. And if you manipulate this equation, matrix equation, we can write it in terms of this positive sequence impedance matrix, which is the inverse of this Y matrix over here. But we will not obtain that using inversion because this may be a 10,000 by 10,000 matrix. So that will be a very laborious, computer intensive as well as error prone because of numerical round off errors and stuff like that would not be the way to go. So in practice, there are procedures to assemble this impedance matrix. Okay, and that is beyond the scope of this course, how that matrix is assembled. But if you can do this for a positive sequence, we can also do it for negative sequence and zero sequence. So these matrices are then used to calculate the fault currents in very large networks. Okay, so we'll just leave it at that. So this brings us to the end of this module where we have looked at transmission line faults. First, the causes of these faults. Then we looked at symmetrical components themselves for fault analysis. We described the type of faults. We have to have the sequence networks for different sequences, and then type of faults would determine how these networks are connected, and we can calculate these fault currents on paper. And then we just saw a glimpse of how they can be calculated in very large networks.